standard normal distribution and how we can use JASP in order to help us find the proportion um, that's represented by the area under the curve, which is the same thing as a probability. So finding proportions and probabilities using JASP. Um, what we're going to do is we're going to add the R console module in JASP. And basically what this does is it uses our statistical software and its functions to help us calculate things. So we actually have access to R without actually downloading the program. It's included as part of JASP. We don't have all of the functionality and capabilities, or at this point I'm not aware that we do. But we have what we need to calculate probabilities or proportions from distributions. Specifically, as it relates to the normal distributions and finding these proportions and probabilities, we're going to use this function here. So one of the things that R has is built-in functions for a lot of things that statisticians need. And so in terms of the normal distributions, if we ever want to find cumulative probabilities or the area under the normal distribution curve, we can use this p-norm function. Now, just like in math, if you've ever taken pre-cal or late algebra, you've talked about not the normal probability distribution, you've talked about functions. And a function is something that takes in inputs and they spit out a single output. That is a feature of a function. And so same thing happens in how RStudio uses its functions. When I use this p-norm, it's telling me to go to the normal distribution. And if I put my value of z separated by a comma, and I'm going to tell R the mean of that distribution. Well, for the standard normal distribution, it is 0. Then I'm going to do a comma. Standard deviation is abbreviated in R or JASP with SD. So I'm going to use SD equals for a standard normal distribution. The standard deviation is 1. And there's this extra little piece here that says, oh, well, do you want the area to the left of this z value, or do you want the area to the right of this z value? If I want the area to the left, I'm going to say lower dot tail equals true. That means it's going to give you the cumulative probability, right? All of the area under the curve for that value and for values that are less than that. All right. It's going to spit out a proportion that is a value between 0 and 1, which is going to be the same as if I asked you for a probability. If we wanted to find the probability or the proportion representing values that are greater than z, then the only difference I would use here is instead of saying lower.tail equals true, I'm going to say lower.tail equals false. I'm not going to use the lower tail. I'm going to need the upper tail, or values to the right that time. One thing about R, hence JASP in this case, it is case sensitive. And so you need to make sure that you spell everything the correct way and that you use the correct case. The only thing that we're going to be doing is separate or changing this z to the actual values that we obtain. So let's go to our example that we got to last time. We were looking at a normal distribution, right? We were in the standard normal distribution, even though this example doesn't say normal distribution here. Well, it's actually here in this part here. Normal with mean mu equal to 115, standard deviation equals to 10. Well, we went through the process of saying, okay, I want values that are less than 100. We said that 100, when we convert it to a z-score, we get negative 1.5. And so we want the area under the curve for values of z that are less than negative 1.5. Negative 1.5 is here on the x-axis, which is now our z-axis. And so we wanted to find this area here. Well, in order for us to do that, we need to use our p-norm function in JASP. And so our p-norm function says, replace that z that I had on the previous slide with your obtained z, and we use this stuff here. So let's go to JASP and let's see which value we're going to get here. Now, one of the things that we're going to need to do is we're going to have to add the module to get us R. In order to add a module, you go to this plus sign here, and I'm going to scroll down until I see right here at the bottom, R console. Notice it added this module here, and this module is different from the others. I know we added the reliability one before. I just took it away since I'm not using it. You could have kept that there. But this one doesn't have a drop down menu, but it's going to open up a box here. And notice it says R is restarting and has selected module, whatever. It's installing this. It's going to, and I've gotten to the point where it's awaiting commands. Now, what I'm going to do is we wanted to do P norm. We had negative 1.5 as our Z. We had a mean of 0, a standard deviation equal to 1, and we had lower dot tail equals true because we wanted the values less than negative 1.5. Once I enter that information in, I'm going to click run code, and I have an error here. It says cannot change working directory. I'm not sure why this happens. I'm going to copy and paste my code here. But if I go to clear output, I'm going to paste that back and run code. It's actually going to work this time. I'm not sure. I think this may be some sort of a bug in the code or whatever of pulling R into JASP. But usually, if you clear out your output and then enter your data again, it may be best that you just clear it when you first start so that you won't run into that issue, right? But basically, this is telling me the area under the curve on the left tail of this distribution for values less than negative 1.5 is 0.0668072. And so that's our proportion of, if I go back to our presentation, we'll see that that is 0.066807. I have it again on this slide. So we can say that the proportion of students who scored less than 100 on the test is approximately 0.067. All right. Now, they didn't ask for the percentage, but if they were to ask for the percentage, you can multiply this value by 100 or move that decimal 2 places to the right, and we'll see that we have about 6.7%. All right. So that's what we're generally going to do when we want to find the proportion of values within our normal proportion of observations in our normal distributions that are covering a certain interval of values. Let's look at another example. Remember we did that example where in week 2 where we had SAT and ACT scores for 2 students, as well as knowing that they had data. Those scales are from a normal distribution, right? The SAT had a normal distribution with a mean of 510, standard deviation of 100. The ACT had a mean 21, standard deviation of 4 for that normal distribution. So we saw that Sam, his score was 560. We converted it to a Z-score. So this is one thing that I want to point out here. Because we hadn't talked about much with populations, I was using our shortcut notation for mean and standard deviation. These are actually population values, but since we hadn't talked about that yet, I didn't use mu and sigma. I would use mu and sigma here. Either way, we're getting the same values here for our Z-score. And then here for Sarah, her Z-score was 1.25. And we said that, because Sarah's Z-score was 1.25 and the scales are measuring similar kinds of ability, Sarah had the higher ability, right? So what I want to do now is I want to look at that same problem, but I want to find the percentile rank of each of those students, right? For Sam and Sarah. Now, remember that a percentile rank, what's your percentile, right? That's the proportion or the percentage of individuals in that population that score below that value, right? So if you're at the 75th percentile, 75% of your population score below that value, right? At or below, right? And so what we're going to do is we're going to find the proportion or the percentage of individuals, and we've already have the Z-score. All we have to do is find the area under the curve of the normal distribution in order to get that percentile rank. So I'm going to start here, right? Sam's score was 560. We converted it to a Z. We got 0.5, right? So if I want to find his percentile rank, I find 0.5, and I need the area under the curve for values less than 0.05. So it would be that area right there, right? Sarah had a z-score of 1.25. So if I wanted to find her percentile rank, all I would have to do is find 1.25 on our z-score, standard normal distribution, and the area under the curve that I'm going to be interested in here is this area to the left here. Notice both of these are both lower tail. They include the lower tail of that distribution, right? So I'm going to go to JASP, and I'm going to do our P norm. So I'm going to come here. P norm for the first person was Sam. He had a z-score of 0.5. The mean for Sam was, well, the mean, it's all standard normal since we changed everything to a z. So we're going to have a mean of 0, a standard deviation equal to 1, and we have lower dot tail equals true. If I run this code here, I get that Sam's score corresponds to an area that's equal to 0.69, right? If I do the same thing for Sarah, her z-score was 1.25. So I'm going to put 1.25 in for z. The mean equals 0. Standard deviation equals 1. And we are, again, since we're talking about a percentile, we're going to have lower dot tail equals true. And if I look here, I'll see that the area under the curve to the left of 1.25 is 0.89 approximately. All right. And so we have this here. So we can say that Sam's score is at the 69th percentile. And then for Sarah, her score is at the 89th percentile. All right. So that's giving us the cumulative probability and only looking at the lower dot tail equals true. Now let's look at the lower dot tail equaling false, right? In this example, let's find the probability that z is greater than 1.33. Let's find the probability that z is, greater than 1.33. I think I said less than, I'm not sure. Well, if I look here, I find 1.33 in my standard normal distribution because we have a z here. 1.33 is here. Notice I have it here, and I want the area under the curve for values greater than 1.33, right? So all I have to do is go to JASP. I'm going to use that P norm function. I don't have to convert anything to a z because it's already a z. And then my mean is 0, standard deviation is 1. But this time I'm going to use lower dot tail equals false. All right. And so let's just do it right quick in JASP. Now I'm going to do something on purpose here. And sometimes I mess up here. So I'm going to do P nom R. So I'm spelling that wrong. I'm going to put 1.33. Mean equals 0. Standard deviation equals 1. Lower dot tail. But this time I'm going to say false. And I'm going to capitalize all of those words. I'm going to go to run. And R is going to give me an error. All right. I did not spell this word correctly. So one of the things about R is that it kind of helps you out when you have some issues. I will say that there are a lot of shortcuts here. Sometimes we don't have to include all this stuff here. I don't want to complicate all of the computations, all of the technology here. So I'm not going to tell you everything that you can do. Like some of this stuff is the default. So I don't have to necessarily type all of this stuff. But the more I tell you, the more likely it is to be confusing. And so we'll just do the same thing each time, convert everything to a z-score. There are ways to do this without converting to a z-score. I don't want the technology to be a hindrance. And so I'm just going to do it this way. If you already know R and things like that, and you are comfortable doing it differently, by all means do so. But my P norm, I changed my code here. P norm, I had left everything else the same, and I clicked run code, and I got this value here. And so notice I changed this to lower.tail equals false. So it wouldn't give me the area below, but it gave me the area above, right? And so if I go back, I can say that the proportion of observations that are greater than z equals 1.33 is 0.0918 or 9.18%. That 0.918 is the probability that z is greater than 1.33. All right. All right. Let's find the area under the standard normal curve, standard normal distribution or standard normal curve to the right of z equals negative 2.46. If I drew my normal distribution, I will find negative 2.46, which is going to be to the left of 0. And I will have to shade to the right of that, right? So I'd get this entire area here for which I want to find the value for. And so I can go to JASP. Again, I'm going to type P norm. I'm going to do negative 2.46. Uh-oh. Mean equals 0. Standard deviation, SD equals 1. And I'm going to have lower.tail equals false once again because I want the values to the right, the area to the right. I'm going to run this code here, and I get a pretty large value, 0.9930531, which when I look at the area under this curve here, that makes sense, right? We have over 99% of the observations are greater than negative 2.46, have z values greater than negative 2.46. So I've done that there, and I say that that area is 0.9931 if I round that to 4 places after the decimal, the 10,000ths. All right. Now, one cool thing about this, right? We just found that the area under the standard normal distribution to the right of z equals negative 2.46 is 0.9931. If I asked, given that you know this value here, if I asked you to find the area under the standard normal curve to the left of z equals negative 2.46, you should be able to do this without using JASP or heavy computer technology. You may need a calculator, but we can find this value. And the reason why we can find this value is that the total area under that curve is equal to 1. And so if I wanted to find the area to the left of negative 2.46, that's this area here under the curve that's not shaded. That's all of the area that's left, right? Besides the shaded area. So if I wanted to find that value, all I have to do is subtract 0.9931 from 1, and I get that that value will be approximately 0.0069. All right, so you can use that information to help you answer questions as well. Now, this last example that we're going to look at is a little more complicated, and so let's look at it. It says a physical education teacher is studying the cardiovascular fitness levels of students in a high school gym class. The fitness level is measured using a running test, where students are timed on how fast they can run a 1-mile distance. The times are normally distributed with a mean run time of 8 minutes and a standard deviation of 1.5 minutes. What proportion of students have a running time between 6.05 minutes and 11.15 minutes? All right. Well, if I want to know the proportion, I have to find the area under the curve between these two values here. Now, I have my normal distribution. It's centered at 8, and I labeled my axes, my horizontal axis in standard deviation units. So I went up 1.5 standard deviations, so on and so forth. And then I've labeled 6.05, which is this point here, and I've labeled 11.15, which is this point here. If I want to know this proportion, I need this area under the curve, right? Well, in order for me to do that, I'm going to go to JASP, and I'm going to convert everything to z-scores. So if I go here, I have z equals negative 1.13. Notice here, I take my 6.05, I subtract my mean, which is 8 minutes. I divide by the standard deviation, which is 1.5 minutes. Do that calculation, I get negative 1.3. That negative sign is nice because I know I'm below my mean. Let's do the same thing for 11.15. Subtract the mean, divide by the standard deviation, we get a positive 2.1. So this is equivalent to going to a standard normal distribution and finding this area here. It looks congruent, but now I've rescaled my data so that everything is in standard deviation units. Now, for me to find this, I've got to think slightly different. Because if I use that p norm function in R, it only gives me the area to the left, right? The lower.tail equals true gives me the area to the left. And then, of course, if I did lower.tail equals false, I get the area to the right. But it doesn't give me any between stuff. So we got to think kind of algebraically, or maybe logically a little bit, about how we're going to find this specific area here. Now, I'm going to start by finding the area to the left of the larger value that I have, right? 2.1 is that larger value of z, right? So if I were to look at that, right, and do p norm 2.1, mean 0, standard deviation 1, lower.tail equals true, I would get this entire area here, all right? Now, I have a problem with this because this area is not the area that I'm trying to find. It includes more area than I need because it includes the area to the left of negative 1.3, right? And so I don't need that area to the left of negative 1.3, so I need to subtract it off, all right? So what we're going to end up doing is we're going to do p norm at 2.1, which includes too much area, and then we're going to subtract off this green area here, which is the p norm at negative 1.3, okay? And so with that, I'm going to go to JASP, and we're going to do that. Now, JASP is like a calculator. It can add, subtract, multiply, and divide. We said we needed p norm of 2.1. Our mean is 0. Our standard deviation equals 1. And our lower.tail equals true. I'm going to subtract from that p norm negative 1.3. That was our z, second z. And I'm going to have lower.tail equals true once again. When I run that code, I get this value here. And so if I go back to our notes, we see that the area between z equals negative 1.3 and z equals 2.1 is 0.8853. Remember, our ultimate goal was to find the proportion of children who had a running time between 6.05 and 11.15. Our answer is 0.8853. All right. And if I wanted to round that to 3 places after the decimal, I'll say 0.885, or that there were 88.5% of children between those two values. And so I'd recommend you doing a lot of those practice problems that I have in Blackboard so that you can get used to, one, the R module in JASP. And also, I always recommend to students, draw the normal distribution for every example that you have. That way you will know which area you're looking for and how to adjust, either using lower.tail equals true, lower.tail equals false, or doing a subtraction if you want the between. All right. And then I may throw an extra example just to make it a little spicy to ensure that we are very comfortable with calculating probabilities and proportions from normal distribution. That's all for this video. I'll see you on the next.